Hi, I'm Sam. I'm going to be talking about Schemata, framework for evolvable schema, a thing we've been working on at Grafana Labs, written in Q. Let's start with a story, the tragedy of Pixas. That's producer, consumer, schema, and instance of that schema. So we've got P, our producer. It is a producer of schema S1. It has an endpoint API, something that accepts objects of type S1. We're not linked to HTTP, but it's convenient to think about HTTP. All right, cool. So we've got a consumer. The consumer, C, is interested in working with this API that P offers. So they import S1, refactor their program, and boom, start producing messages and sending them over to P. Everything's good until, whoops, P changes the schema, blows everything up for C. Now they've got a new thing that they're expecting, and C is broken. C can't really do much except refactor and catch up. Problem there is this requirement of coordination, really. C would have had to know beforehand that P was going to make this change in order to avoid having the problem in the first place. Coordination is expensive, so we want to avoid it. Now, how can we do that? Well, P has some options. P could make an externally versioned API like this one. Think HTTP. The standard here is you make a prefix on your new changed paths, and then great, you know, old messages still work. The other option is an internally versioned API, where all the complexity is packed into something at the endpoint, and then P just works with the version that it wants to. Now, that's nice, except that realistically, that complexity can get spewed all over the inside of the P program. And actually, when C refactors to catch up, it can get spewed all over the inside of C as well. So the question is, how can we crisply contain translation at the program boundary? And Schemata at the minimum components necessary for a general solution to this problem. All right, let's talk architectural quanta. An independently deployable component with high functional cohesion, which includes all the structural elements required for the system to function properly. That's what we want. We want this for schema. That's what Schemata is supposed to be. It's supposed to be the quantum of schema. Sorry, not sorry. Let's talk about the elements of schemata, okay? Schema, we know what those are. Lineage, they're sequences of backwards compatible schema. Lens or translation, they're mappings between schema. Lacuna is a gap in translation, and a family bundles them all together. So a schemata family, say we've got 4 schema, 2 in one lineage, 2 in the other, and backwards compatible within each lineage, but not across them. The lenses map between the lineages. Cool. All right, let's talk about what we actually do with that. So we've got our program. Schemata-based program. It's got an object, an S of type 00, validated to be so. Well, we could translate this. That's really what we want to do with our program, to have all this translation happen right at the edge. When we translate, we get the object out that we want, as well as lacunae that describe any possible problems with the translation. Now, there can't be any problems when we're making a backwards compatible translation like this one. But once we cross that boundary, there can be. So lacunae there identify any issues that may have existed in this translation, and we accumulate those lacunae no matter how far we want to push our translation along the series of schema within the family. There is a bunch of invariants that make this possible in general, but we're not going to talk about those. This talk's too short. So instead, we're just going to talk about what we get from them. Always translatable. Program relying on schemata can always translate a schemata validated object to the family's latest schema. Lacunae should be sufficient, we think, for all possible remediations a program would need to make, including failing if the changes are, if the translations are too inaccurate. Reliable and trivial publishing because of how simple and encapsulated schemata are, and crucially, evolutionary decoupling. That is, systems communicating through these schematized contracts within limits can safely evolve over breaking changes without coordination. So let's talk about what that looks like. The implications, back to our tragedy of Pixas. Here's where we left off. We have complexity spewed all over the place in C and in P. If we're using schemata, though, this does what we want. It encapsulates that complexity at the boundary for P. Great, okay. But it also applies to C equally well. There's no reason that C shouldn't be able to use schemata in the same way. A bunch of interesting degrees of freedom here. Don't have time to talk about them more. Let's talk instead about infra as code. Kubectl. Kubectl, relatively dumb, actually, when it comes to knowing whether or not the objects that it's sending along to the Kubernetes API are correct. It relies on the Kubernetes API for that. If Kubernetes published its schema with schemata, though, Kubectl could, of course, do the translation if he's got a heterogeneous set of objects like this, but it could also do the translation right back on disk without needing to consult the API server at all. In Grafana's case, we have a tool somewhat like kubectl, somewhat analogous, we call Tonka. Now let's imagine that these files here are actually Grafana dashboards, 10,000 lines of JSON, composed of a bunch of different schema from a bunch of different components, and we ultimately want to have them land in the Grafana instance. Well, one of the things that we might want to do is have a query validator. These dashboards contain a bunch of queries. We'd like to know that those queries are valid, but our query validator is old. It doesn't matter. In a Schemata world, we can translate to have all these different programs be expecting things at different versions with heterogeneous inputs, and all of them can basically function. That is the promise of evolvable schema and evolutionary decoupling. Thank you very much.